Hello, Mr. Claudia here. Today we are going to continue our study of probability distributions by looking at the normal distribution. So far we've learned how to look at discrete probability distribution tables. This normal distribution, our second distribution we're going to look at, is for measuring continuous random variables. So to introduce, this is also a long lesson, so get ready. To introduce the normal distribution, let's look at test scores. So I have a random variable x, which is your mark on a test, and I have all these different ranges, 40 to 50, 50 to 60, and you can see how many students were in each of those ranges. So one was below 50. I have my modal class is between 70 and 80. That's where I have the most number of students. So let's say I was going to graph this on a histogram. I can do this quickly, but this would be 50 here, and I have 40, 60, 70, 80, 90, 100, something like that. 30, 20, 10. And I guess I should get a ruler, and I'm going to very quickly draw this. The highest number is 8, then I have 4 here, 2, and 6. So for between 40 and 50, I go up to 1. Between 50 and 60, I go to 2, then 4, then 8, and then 4 again, and then 2. I'm just going to draw this histogram. Okay, and there's 100%. So I've just taken that single variable, the mark, and I've drawn a histogram. And we see that most of this, well, sorry, let's also, I didn't get you to write this down, I've already given it to you, but the mean, well, I can find the mean by multiplying the middle value of each interval by the frequency, dividing by the total number of students. I get an average or mean of 73. So that's the average. In other words, this is the central value, which we learned in the statistics chapter. Then I can find, do you remember this? Sigma squared. This is the variance. I take every measurement, subtract it from the average, and multiply it by the frequency, which I did not show. And then I add them all, I divide by total number, and I get the variance. This is a measure, if you remember, of how spread out the data is. We don't like the variance too much. We usually tend to take the square root of it, which is the standard deviation. So hopefully you remember doing these things in the statistics chapter. Great memories. But when I graph all this data as a histogram, I get this shape, right? And the shape happens because most of the students tend to be in this range from 70 to 80. Then as you go higher or lower, the number of students drops off. This low mark, this failing mark, that's the lowest number of students in that area. If I were to put a dot at the midpoint of each of these boxes on my histogram, and I drew a smooth curve through all of the midpoints of the bars, I would get this characteristic shape, this bell curve. And that is the normal distribution. So formally, the normal distribution is the most important distribution for continuous random variables. A lot of things in the real world follow the normal distribution. Let me just draw it first so we can kind of see it when we talk about it. I want to make a really nice one here. Not bad. Okay, there we go. So there's the normal distribution. It has a characteristic bell curve, we call it. So that's why we often you'll hear this term, especially when you're talking about university courses. We'll talk about moving the bell curve. a lot of things follow this. So remember, just like when I was looking at your marks, the normal distribution, the central value occurs the most, right? That is actually the mean. So the normal distribution is centered and it's symmetrical about the mean. So that's my first observation. Symmetrical about the mean. The second thing you'll notice down here is that on both sides there's an asymptotic behavior. Here, as x approaches infinity, positive infinity, f at x approaches 0. So it's an asymptote. I guess it's a horizontal asymptote. So that's part of this shape as well. Not only is it symmetric, but it also gets closer and closer to 0. Finally, and this is going to come up later, but the area under the curve is equal to 1. Not to stress you out too much, but that means that the integral from negative infinity to positive infinity of f at x dx is equal to 1. But don't worry about that. That's just, just to remind you what area is. That's the 3 characteristics of my bell curve, or sorry, my normal distribution. We have a central value where most of the population lies, and then it drops off as you get further away, just like with the test scores. This phenomenon, the reason it comes up so much is a lot of things follow this phenomenon. So anytime you're looking at physical attributes, it follows the normal distribution. So that would be height, weight, shoe size, arm span, blood pressure. If I were to measure everyone's blood pressure in this class, most of us would be around an average, and then we would drop off. Some would have higher, some would have lower. Test scores is a big thing for this. What else? Income distribution. Most people are around the average, and then there's some very rich people and some very poor people. What else? Reaction time. Measurement error. So if you were to measure something, you'd be off. On average, you'd be, or you'd have an average amount, but then sometimes you'd be really off, too small or too large. So measurement error. Normal distribution is all over the place. So this is what we're going to be using for this entire lesson. Now, do you want to know the formula of this curve? Well, we call this the probability density function, and it is f at x is equal to 1 over sigma root 2 pi e to the negative half x minus mu over sigma squared for x's between positive and negative infinity. That's easy, right? No, it's not. This is a terrible looking question, right? It's an e, so it's exponential, natural exponent. It's got all these variables. It's got all these variables in front. It's gross. But one thing you notice is that it's a function based on x. The only other variables are, okay, pi is just 3. E is a number, 2.7. So the only real variables here other than x are sigma and mu, which we know, right? Sigma is the standard deviation. And mu is the mean. So what we're going to find is we're never really going to use this formula. I mean, I should put in your notes for definition of the math of where this comes from, but we're never going to use this formula. It's built into your calculator. what we are instead going to do is say that a random variable x follows the normal distribution with these parameters, mu and sigma squared. So we're only ever going to note these two parameters because they're the two variables we need to define this curve. So every situation, the curve is a little bit different based on these two parameters. So that's what I call them. You'll notice the parameters are the mean, mu, and sigma squared. It's actually the variance that we write here. Now, before we go on to actually solving some questions, we should talk a little bit more about this. The normal distribution, that curve, no matter what your parameters are, no matter what your mean and your standard deviation are, the area always divides out or always ends up looking the same. So if there's my central point, my mean, 68.2% of the area, or 68.2% probability that you're going to be plus or minus 1 standard deviation from the mean. So if we want to look at it in terms of area, 68.2% of the area is mu minus 1 standard deviation and between u plus 1 standard deviation. Then if you go 2 standard deviations away, those two sides both have 13%. And as you go, so you could say that 95.4% or 95.4% of the area is mu plus or minus 2 standard deviations. And then again, any situation with normal distribution, 99.7% of the population is plus or minus 3 standard deviations. If you want to go back to this question with your marks, this means that 99% of students should be the mean, which is 73.6, plus or minus 3 standard deviations, which is about 36. So 99% of the data should be between 109 and 37 or whatever, which is correct. So that's the way the normal distribution works. If we use it because we know we can make predictions using this information. Now this idea of 68, 95, 99, this is now something that's in IB, so you should be aware of these percentages. You should know, vis-a-vis, you should memorize these percentages because we're not really sure, but we know that it's been added into the IB curriculum. So I wouldn't take any chances. I would make sure I know those. If all normal distributions have this property, then now I can use the normal distribution to make predictions. So let's look at a starter example. The mean height of players in the basketball competition is 184 centimeters. If the standard deviation is 5 centimeters, what percentage of them will be taller than 189? So because we're talking about a height, a physical attribute, I suspect it follows the normal distribution. So I'm going to sketch my normal distribution bell curve. Try to do as nice a sketch as I can. Every year I get a little bit worse. Okay, so the mean is 184. Remember, mean is the central value of my symmetrical standard deviation curve. Now, I can draw a sort of related standard deviation. I can now sub this in with real values. So my mean was 184. My standard deviation is 5. So I want to go 1 standard deviation up, 1 standard deviation down. So I'm going to go up to 189. That would be 5 centimeters up. And then I'm going to go to 179. So if you want to think about it, this is mu plus sigma, this is mu minus sigma. I can keep doing this, right? 189, the next one would be 5 up, so it would be 194, 199, etc. This is mu plus 2 sigma. This is mu plus 3 sigma. This is 174, and this is 169. And this is mu minus 2 sigma, mu minus 3 sigma. I just want you to get an idea of what this looks like. Okay, and now I can also, so from this I can map these areas. So this is 34.1%. This is 34.1%. What's this one? 13.6%, 2.1%, and this is very small now, 0.1%. 13.6%, 2.1%, 0.1%. Okay, so all of the areas, because it's a normal distribution, all of the areas can be predicted. Now we can make predictions about the probability that a player will be taller than 189. So what's the probability that random variable x is greater than 189? Well, here's 189. So the probability that you're taller is 13.6 plus 2.1 plus 0.1. Remember, all of these area adds up to 1, just like all of my probabilities add up to 1. This, of course, it never touches the axis, but it's such a small area as it gets closer and closer, eventually it becomes negligible. So if I want to know the probability that somebody is taller than 189, I just add up 13.6, 2.1, and 0.1. Again, the word on the street is that you need to know these percentages or have an idea of them. So that gives me, what, 15.8%. 0.158 or 15.8% chance. Right? Okay, now part B, what's the probability that a player is between 174 and 199? So the way I would write this, the probability, and then I write it as an inequality statement. So 174 is the lower bound between that and 199. In a similar way, I just add up all of the areas. So 13.6 plus 34.1 plus 34.1 plus 13.6 plus 2.1. Well, it's pretty much everybody, right? It's a pretty high percentage. That's 97.5%. And this makes sense, right? If the average is 184, the probability that you're going to be between 174 and 199, that's most of my players. Part C, what is the probability that somebody is less than 174? Well, that's these people over here. They're less than 174. The probability that X is smaller than 174. You do have to be good with your greater than or less than symbols in this section, right? X, it would, if you remember this, the teeth would rather eat 174, so X is smaller than 174. This is going to be 2.1 plus 0.1, that's 2.2%. So the probability that people are going to be less than 174 centimeters, which is what? 174 divided by 30 is 5'8". No, well, 5.8 feet. So a very low probability of basketball tournament of being that short, because the parameters, the mean and the standard deviation for those players, well, it's a higher average because basketball players tend to be taller. Although that's changing, right? You could write a paper on that. Okay, so remember, so that's one way of solving a question, right? To make a diagram and to lay out all of my areas which are fixed or the same for all types of questions. Now, this normal distribution is going to change based on those two parameters. Reminder, the two parameters are mu, which is the mean, and sigma, which is the standard deviation. How does the bell curve change with these two values? Well, changing the mean, changing mu, moves the bell curve left and right along the axis. So for example, if this is my bell curve or my normal distribution, x1 is a normal distribution with average 5 and a standard deviation of 2, then it would be a bell curve centered on 5. So remember, x is a random variable. It follows a normal distribution. The first number is the mean. The second number is the variance. We always write the variance, though, as a standard deviation squared. This is so it's clear what the standard deviation is, but you do have to write it as 2 squared. It's technically a variance. Now, if I wanted to plot x2 is a random variable that follows a normal distribution, but this time the average is 10 and the standard deviation doesn't change. The shape of the graph is the same, I've just moved it up. Because now the mean is 10. So the curve is in a different location. Moving the bell curve. So if you think about if I went to art class and drew the bell curve for heights in art class, it might be the same shape, but it would be way lower, right? Because we're probably on average a lot shorter. This is something that moving the bell curve is something you'll hear about in university. If you get a really hard midterm, or really easy midterm, and everyone's mark is too high, the bell curve of all your marks is too high, you might get a really tough final exam, which is an attempt to lower the bell curve so it's at an average that the professor's happy with. So often in university, you don't really care about necessarily what your mark is, you're more concerned about where you are in the bell curve. If you're way above the average, then chances are, if you can maintain that position, that's more important than what your final mark is. Okay, now what if we change the standard deviation? Well, okay, let's draw a bell curve or a normal distribution. Ooh, that was probably my best one. So this is going to be centered at 5. So this is x follows a normal distribution, average of 5, and we'll say a standard deviation of 1. Okay, if I change that standard deviation, the position of the graph stays the same, but the spread changes. So if I were to have a larger standard deviation, remember standard deviation is how far away from the curve you are, or from the average, the shape tends to change like this. So it gets flatter, I guess you could say. So that's what happens if I change my standard deviation. And if you look for all of these, they all still follow this rule. That is, the 68% of the area is between mu plus or minus 1 sigma, 1 standard deviation. It's just that now, the standard deviation is bigger here, so and the whole thing is a lot squatter. But it's the percentages still work out. Okay, let's keep going. Now, traditionally, like when I took stats in university, when you take stats probably, and when even your friends who are taking a non-IB program at the school, at data management, they would have to look up normal distribution probabilities using a table at the back of a textbook. So here's my engineering statistics, first, second year stats book. And here's, it has a bunch of distributions in the back, stats, like different distributions. But this one is the one we want. It's called the standard normal distribution. And this is where I would look up areas. I'll show you how this works in a little bit. Oh, but look, there's the formula. Now, it's impractical to have a different printed table for every set of parameters. Imagine, you'd have to have a printed table when the average is 184. You'd have to have another one when the average is 185, another one when it's 186. Like, it would take forever, and it would take up a lot of paper. So instead, what we do when we do a stats class is we define a standard normal distribution. This is the one version of the normal distribution that we can look up in the back of a textbook. It is a normal distribution where the mean is 0 and the standard deviation is 1. That's called the standard normal distribution. And it's centered on a mean of 0, so it's centered on the y-axis. So it looks like that, or something like that. So my standard normal distribution, we call the random variable, in this case it's always z. Z is the way that somebody knows, if you're talking about z, you're referring to a normal distribution with parameters 0 and 1. 1 squared technically, which is 1. Again, why do we have this? The reason for a standard normal distribution is that's what's in the back of your stats textbook in university or in a regular grade 12 program. And I'll show you how this works in a second, but this is the one. You can see it has z. It's a standard, it's a normal distribution centered on 0, and look, it's the area of that curve, right? Remember, that was the curve I showed you. So what we can do now is we can find probabilities, make predictions about certain values that aren't necessarily exactly one standard deviation away. In this question, it was easy. I was looking at for the number 189. Well, 189 happened to be one standard deviation up. What if I wanted to know the area, 186, for the area above 186? Well, that would be harder to do because I don't know what the area is if I cut that in half. But I'm going to show you how to do this using a table and using your calculator. So what is the probability here what's the probability that z is less than or equal to 1.5? So what this is saying, what's the probability that z is less than or equal to 1.5? This is saying what is the area under the standard normal distribution from negative infinity to up to and including 1.5. So if you want, and what I always will recommend is you sketch this, right? It's very, it will always help you understand the question. So first of all, that z should be an indicator to us right away, indicates a standard normal distribution. So that means that it should be a normal distribution centered on the y-axis. So this distribution is z, such that it's a normal distribution with mean 0 and standard deviation 1. Okay, now we want to know the area under the curve, the probability that z is less than 1.5. Well, if this is 0, 1.5 is somewhere up here to the right of 0, right? I don't know where, I'm just doing a sketch. And we want to know the probability that z is less than 1.5, so we want the area of this, under this curve, between negative infinity and 1.5. Okay, to figure this out, if I was taking a regular grade 12 program, I would now have to look this up in my book. So the area less than 1.5. So the way this worked is z, was 1.5, so I have to go to page 2 here. 1.5, and it was 1.50, so this tells me my tens column, my hundredth column. So it's 0.933. So then I would write my answer. Approximately 0.933. So there we have just used the normal distribution, the standard normal distribution, to make a prediction that random variable z is less than 1.5. It's a 93% chance. My sketch is a little off. Technically this should probably be further up, but we got the idea. This 1.5, this is frequently called the cutoff. And this side over here is called the tail often. Just some terminology. Now, one last thing to note is that for a normal distribution, because it's continuous, the probability that z is less than or equal to 1.5 is the same as the probability that z is less than 1.5. So that's an important distinction to note. There's no the less than or equal to or less than sign. It's essentially, practically, they're the same. Now, in our lives, we have a GDC we're going to use to do this. We don't actually get the tables anymore. You guys have a GDC that can do all this for you. And it's pretty straightforward to do this with your calculator. I'm going to turn on my calculator, which is kind of turn its light off maybe to help. No, it's hard to see. And I'm going to press, what am I going to press? Go to calculator mode. So there's my calculator page. And I'm going to press menu, statistics, and then I go down to number 5, which is distributions. And I'm going to choose normal CDF. Very important, we never choose normal PDF. We always go number 2, normal CDF. It stands for cumulative distribution function. Cumulative meaning we want all the area up to and including a certain amount. So we'll never use PDF. Now I have to enter my lower bound. Well, you want to enter a very large negative number, negative infinity. You can't type infinity into the calculator, but you can put a negative large number. So we put negative 9, that E999. The way we would type this would be negative 9, and then E is actually this button here next to the letter A, E, and this means times 10 to the 9999999. So this is basically saying negative 9 times 10 to the 99999, which is a humongous negative number. You could just type negative 9999999. That's a large number too. The upper bound is, in this case, that cutoff of 1.5. And look, it's already put in the parameters 0 and 1 for me. So I just press enter. Oh, that's too much for my calculator. Okay, I'm going to change that number to negative 999. There we go. And sorry, I shouldn't have put negative 9E999. It's too many. It was too much for the memory of my calculator. I just put negative 9999, and there's my answer, 0.933. So my calculator does all this for me. We don't use the tables in this course. I will just note here what this is. So this is the lower bound. This is what you type, but it's really negative 9 times 10 to the 999. Don't put more 9s like I just did, or you're going to overload your calculator. This is the upper bound. This is mean, and this is standard deviation. This is what you type. Type in the GDC. Do not write this on an exam. IB really doesn't like when you write calculator language. They want you to write math. So if you're going to write anything for part marks here, you're going to write math language, make a diagram. But nobody is going to give you any marks for writing what you typed in your calculator. This is something you need to know, but you're never going to write. Okay, so now let's look at some more difficult questions. Again, for all of these, I find it very helpful and there's a great way of picking up method marks is to draw a sketch. So in this question, we want to know what's the probability that the member Z is the standard normal distribution. So here, let me draw that right away. I know it's this characteristic bell curve shape, but it's centered over the axis. What's the probability that I'm between negative 0.41 and 0.67? Well, if this is 0, 0.67 is somewhere to the right of the axis, and negative 0.41 is somewhere to the left, but not quite as far over. It's just an approximate sketch. We want to find the probability that Z is between those two. So we want to find the probability of being in this space. So we want to find this area. The way we do this is we have to, well, we can use our calculator, because look how powerful our calculator is. I press menu, statistics, oh, sorry, don't do that. And we go to distributions, normal CDF, always. The lower bound in this case, well, the lower cutoff is 0.41, negative 0.41. The upper cutoff is 0.67. The parameters are 0 and 1, because this is a standard normal distribution. I press enter, and it gives me my answer. And I should always round to 3 sig figs. So this is 0.408. That's it. So again, if if this is worth 2 marks, like, it's useful to draw the sketch. If you made a mistake then entering it into your calculator, you would get a mark for the sketch. And it helps me understand the problem. This question is asking, okay, what's the probability that the standard normal distribution, so it's this characteristic shape, is greater than 0.84. Okay, so this time we're talking about a cutoff of 0.84, so somewhere to the right. We're saying what's the probability that Z, random variable Z, is greater than 0.84. So we're talking about this area here. Now if we use our calculator to do this, menu, statistics, distribution, normal CDF. And we're going to put a lower bound of 0.84 as the cutoff. Now the upper bound, we have to put a very, very large number. Again, you can't put positive infinity, you just put a very large number. And then the 0 and 1 are the parameters. And that gives me my final answer, 0.200. So our calculator, this exercise is really about using our calculator effectively. Now, if you're curious, how did we solve this before the calculator? Well, this one, here, I'll just make a note down here. Without the GDC, this question would have been, to solve it, I would have had to do the probability that Z is less than 0.67 minus the probability that Z is less than negative 0.41. If I look that up in my tables, so 0.67, so there's 6. So 7486, 0.7486 minus the probability Z is less than negative 0.1. That's on this side. Negative 0.41 is here, 3409. And then again, I wouldn't have my graphing calculator. I'd have to do it this way, 0.7486 minus 0.3409, and that gives me 0.408. So I get the same thing. It's just more work. So really what you had to do is look up the area below 0.67, subtract the area below negative 0.41, and then I'd be left with this area. For this one, without the GDC, I show you this just because it is a useful thing. You'll see later why this is useful. If I want to find the area, my tables only show the area below a cutoff. So if I want to find the area above, I have to use the complement. This is 1 minus the probability that Z is less than 0.84. And again, I'm showing you this for a reason. But if I want to find the area above 0.84, I basically am finding this area from my table and subtracting it from 1 to find this area. So I can go to my table. What's the probability that Z is less than 0.84? Did we do this one already? No. 0.8. 1, 2, 3, 4. 0.7995. I subtract that from 1. And I get 0.200. So luckily you guys don't have to do this with the table. You can just use the calculator. The calculator is super powerful. And really this section is all about learning the calculator. Okay, home stretch here. We're going to learn a way to translate or to transform any normal distribution into a standard normal distribution. To do this, we calculate something called the z-score. The z-score is equal to the variable minus mu over sigma. I'm going to put that in a box. The z-score calculation is useful. Because here's the thing, the questions we just did are all talking about standard normal distributions. But in real life, numbers don't, the parameter of most normal distributions, they aren't so nice. The mean is not necessarily 0, the standard deviation is not necessarily 1. So we need to be able to take any normal distribution and transform it into a standard normal distribution so that I can look up my answers in the table. The traditional way I would have solved a normal distribution problem, again, without the GDC, would be to draw a normal distribution for my question, then transform to a standard normal distribution. And then once I'm in a standard normal distribution, I can read the probability from the standard normal distribution table. Oh, there it is. Okay, so that's how I would normally do a question. So let me show you how we would normally do a question like this. So a real life question. So traditionally, Mr. Colley's classes have a mean of 68%. Oof, not an IB, usually a lot higher, and a standard deviation of 10. Assuming that the test scores are normally distributed, what is the probability that a student scores less than 40%? So I'm going to draw a sketch. That's what I always do when I have a question like this. Now this is not a standard normal distribution. This is just a normal distribution centered at 68. If I wanted to write it, and this is good to write this in this form, this is worth a method mark. X is a random variable that follows the normal distribution with parameters 68, that's the average, and the standard deviation is 10.2. So I write 10.2 squared. Again, we have to technically put the variance here, but to show that, to make it easy for me to know what the standard deviation is, I put 10.2 squared. Okay, and yeah, I'll just put a little note, right? This is the mean, and this is the sigma squared. Okay, and the question is asking, what's the probability that a student scores less than 40? So 40 is somewhere here, that's my cutoff. And I want to know if a student is less than 40. So that's the area I'm looking for. Now, traditionally, again, I can't look this up in my table. My table is only good for a standard normal distribution. So what I'm going to do is transform it into a standard normal distribution. Again, why are we doing this? If we have the calculator, it'll come up in our next lesson. This is a useful thing to talk about. So this is now Z, which follows a normal distribution of 0, 1. Those are my parameters. And this cutoff, like this area, we're still talking about an area here, but now the cutoff has changed. It's no longer 40. It's some negative value. To calculate the cutoff, I have to use my z-score formula. I have to write Z is equal to, okay, the mark, which was 40, minus the average, which was 68, divided by sigma, which is 10.2. If I type those things into a calculator, where's my calculator? I have 40 minus 68 divided by 10.2. That gives me negative 2.745. So in my new world, my standard deviation world, this cutoff is no longer 40, it's now negative 2.745. So I could write now the probability that x, standard random variable x, is less than 40. Well, this is the same as the probability that standard random variable z is less than negative 2.745. Right? This is telling the marker I've transformed into a standard normal distribution. And now I could look this up in my table. What is it? Negative 2.745. .003. So 3% chance, whoa, 0.3 chance that you're going to get below 40. Wow, that's good. See, most students pass. Does that mean all students, that there's never going to be a student below 40? No, it's just a prediction we're making. So this is how I would have done it traditionally, right? Draw the normal distribution, transform it to a standard normal distribution, look up the chart value. Now you guys, well, your life is so great. You don't even need to do this. You can just draw the sketch and use your calculator. Menu, statistics, distributions, normal, CDF, always. The lower bound here is negative infinity, so I'll just leave that, negative 9E999. The upper bound is this cutoff of 40. The mean, well, it was written right here, it's 68. And the standard deviation is 10.2. Notice I want the standard deviation, not the variance in this case. Press enter. And it spits out my answer, 0.003, which is what I got from the table. So for your IB, with your amazing calculator, you don't even need to do this transformation. you just can put the parameters right into your calculator. So for this last question, what's the probability a student scores between 70 and 80? Well, I would draw my sketch. Again, the sketch is worth a mark. It helps me understand the question. 68 is the middle value. So we're talking about the students between 70 and 80. This is 70, this is 80. And we're talking about the students in between. This curve is a random variable x following a normal distribution with parameters 68 and 10.2 squared. It's a good idea to write that line out. That's worth a method mark if you make a mistake. Just going to make a note. With our advanced GDC, we can skip the z-score step and input mu and sigma directly into our GDC. So you can actually just write the line, the probability that x is between 70 and 80. Just going to type that into my calculator directly. So we're going to go calculator mode, menu, statistics, number 5, distribution, normal CDF. My lower bound is 70, my upper bound is 80, my mean is 68, and my standard deviation is 10.2. Press enter, and there's my answer, 0.303. So that's using our GDC. Incroyable. So our GDC is very powerful and allows us to skip a lot of steps. I hope you can understand what we're doing here, though, because it will come up in our next day's lesson. Okay. The last thing here you can read on your own time, but often in science when you're checking to see, you're doing a study and you want to see if something has had a significant effect in your study, you will do a variation of the normal distribution. We call it the t-test. You define a null hypothesis, so some situation where nothing has happened. So the heights are, this is if you're comparing sun shining on your garden. So you wonder, okay, if I put some of my tulips in the sun, will the sun make them grow higher? So you have to, what you would have to do is measure the heights of the tulips on each side of the garden and then compare your data. Now the heights would technically follow the normal distribution. So comparing heights, averages, comparing spread is one thing, but it's better to compare the normal distribution. So for example, if this is the heights of my tulips on the right side of my garden, the heights on the left, to know if the sun really had an effect, I'd want to compare normal distributions. To do this, we define a null hypothesis. That is if there is no effect or nothing happens. So the heights are the same from the left side and the right side. The alternative to this is that, yes, the heights are not the same and there was some sort of noticeable effect. Now, for this to be in science, we need to choose a cutoff for this for the results to be significant. So often we say, okay, if there's a 5% difference in the heights here versus the heights here, then I will say that they are not the same, and my alternative hypothesis works out. Otherwise, my null hypothesis is true. You can actually do this with your calculator. You can go into menu, statistics, and go down to your stat tests and run a t-test. And you can enter all this data and then run a t-test. And what it spits out is a p-value. If your p-value is greater than the significance, I remember I said it's 5%, then you accept the null hypothesis, the sun didn't have an effect. If your p-value is less than the significance, then you reject the null hypothesis. It actually is the alternative hypothesis. This is not really in the course, but it's a useful thing for science. And your science teachers have actually asked me to include a little bit of this in the course, so that's why I put it here. But if you're doing a test in biology, this is kind of the process. Now, this significance, 5%, not a huge difference, and there is some discussion in the science community, should this number be greater, 10%, 15%? Is just looking for a 5% difference really enough to tell if something has had effect on something else? Anyways, that's a very short talk about the t-test, but that's something that you might be using in your science world. It's not in our course. What's in our course is the normal distribution, and all of this homework in this massive section that we just did. So our homework is page 541, number 1 to 7, page 543, number 1 to 3, and page 544, number 1 to 5. It's a long lesson. There's lots of things here, but it's all with a GDC, and you'll find you're just basically playing with your GDC and be learning how to do this very quickly. I will also just say that let's say you don't have a GDC and you want to use another online resource. You can't use Desmos. Desmos can't do this, at least not yet, but you can use something, a very powerful graphing calculator or online calculator called Wolfram Alpha. This is at www.wolframalpha.com. Very powerful. You might find you're using this in university. It's so there's so much in this. I've only scratched the surface. It's very advanced math. But for Wolfram Alpha, you would type, to do this this first example, you would type normal CDF and then the parameters. So what did we do here? Negative 999, 1.5, 0, and 1. So it's pretty much the same thing. It's normal CDF, and then this is the lower bound, this is the upper, this is the mean, and this is the standard deviation. So if you don't have a GDC at home, please, for the homework, use Wolfram Alpha. It's not helping you get ready for the exam, but at least you'll know if you got the right answer. So play around with that. It's very powerful. Good luck, and we'll see you next time.